welcome to ATS 115, Applied General Chemistry. As you are probably well aware, this course is required for the Chemical Laboratory Technology program, into which you've already been accepted. I am the director of that program, Dr. Diane Thomas, and I will also be the instructor for this course and the scientific math course. My office is Norman K. Myers building. That's on the Springfield main campus, room 223H. You'll be on that campus on Fridays for lecture and labs. So when we meet on Fridays, or the first Friday, I can show you where that office is. We can find that for you. My office number, 417-447-8809, or you can email me at thomasd@otc.edu. That is in the syllabus. Office hours are in the syllabus, but since this is a hybrid course, you're probably only on campus one day a week. Those times may not work for you. So if you ever need to meet with me on a Friday when you come in, just let me know ahead of time, set up an appointment, send me an email, give me a call, or we can do things via email on the phone, whichever works better for you. Just want to let you know about the items that you're going to need for this course. You do need the textbook. It's Introductory Chemistry by Tro, 5th edition. It is pictured, the cover of it's pictured here on the right. You do need it with the Mastering Chemistry add-in. So any format of the text is acceptable. You can get the hardcover text, you can get the loose leaf 3-hole punch text, or feel free to get the ebook if you are comfortable with electronic format. I believe the ebook is probably the most economical, but I know some people like to have that copy in hand. So any format you want is fine. Just be sure that you do get it with the Mastering Chemistry code, otherwise you will have to purchase that additionally. You are going to have access to Blackboard, of course, which you do have as a student at OTC, and there's another site that is not absolutely required, but it is one that I'm offering sort of a bonus for checking out, Conceptual Chemistry. This goes along with another textbook and another whole series, Conceptual Science. So the author of that book, John Suhaki, has been talking with me about the possibility of using it for the course. And so we're kind of testing it out this semester to see how it works. So the work that is done there will be offered as sort of a bonus. And we'll talk about that more via the Blackboard site or when I see you in person on Fridays. You will need a scientific calculator. If you have a graphing calculator, already, that is totally okay, fine to use. Not necessary to spend that much money. Just a very inexpensive scientific calculator is fine. Just make sure that it has log functions on it. So make sure it's not a business calculator. Those you can get for around $10 or so at Walmart now. Casio TI 35, something along that line. If you have any question if your calculator works or not, let me know. If you really just can't get a calculator right now, let me know. I have some that you could borrow for the semester and then turn them back in at the end. And then you'll also need a pair of laboratory-approved chemical splash goggles. So these must be designed for use in a chemistry lab, designed to keep liquids out of your eyes. Now, I just want to take a minute and go through these two sites that I talked about. If you're not already familiar with Blackboard, just to let you know, when you go to the OTC website, you will click on My OTC. And when you get into the first page, you will go to the sign in. You will put in your ID, your OTC username, and your password. Same one that you use for accessing your email, anything like that. You do have to click sign in, otherwise it won't take you there. And we wait for that to load. Once you're into the My OTC portal, you see all these tabs across the top, and the one you're looking for is right here at the end, the Blackboard site. Once you've got that, you log into Blackboard. If you want to bookmark this site, it will just take you to the login page for Blackboard, and you won't have to go through those additional steps. When it opens up, you will see a list of courses. You won't have the ones where you're an instructor probably, but you will have courses where you are a student, and you just need to find the one that says 15 Fall ATS 115 Applied General Chemistry. You can click into that, and you will start with a welcome page. Announcements will always be the first thing you see when you come into the site. There's some information about me as the faculty. Here's a link to the syllabus, schedules, calendar. Here's where you'll find the labs each week as I post those, weekly lessons. Occasionally we'll have discussion boards. This will be more likely weeks where we don't meet on Fridays, so it's just a little additional talking back and forth that we can have, sort of talking via the website. Various resources, you can find your grades here, so on and so forth. Now note that there's some buttons down here I have that you will not have. Also, you will find that not everything for the whole semester is there yet. This is a new course in development, and as hard as I'm trying to get ahead of you guys right now, I'm only a couple of steps ahead of you, so please be patient as I work on posting things here. But you can go through the Blackboard site. When you start with the welcome, it will give you directions on where to start and go through. Syllabus, schedule, and calendar. Once you've finished with that, you can go on down to the first weekly lesson. And under the weekly lesson, you'll have some information available to you, getting to know the neighborhood. Not available just at the moment because I am working on this presentation right now that has to go into that. As soon as that's in there, you'll have it available to you. So it'll look a little different when you're looking at it. Okay, so now we come back to this. All right, so let's talk a little bit about the information in Chapter 1, the chemical world. Most of the information in this chapter is probably a review to you if you've ever had any sort of a basic earth science class or basic science in middle school. Is supposed to cover most of this, but we do want to just cover a few things and define specifically when we talk about chemistry, what are we talking about? What chemists try to do is understand what matter is doing by studying the atoms and the molecules. Okay, so if you're not familiar with these terms, atoms, molecules, matter, we'll look at that a little bit more in a minute. Okay, but be aware that virtually everything around you is composed of chemicals. And this is one of the pet peeves for a lot of chemists, is when people talk about chemicals in a broad term as though all chemicals were bad. Chemicals are not good or bad. It's their interactions with things that are good or bad. And not every chemical has a bad interaction for us as human beings. So, for example, someone says, Doctor, do you recommend a chemical-free diet? Only if you'd like to starve to death, because everything you eat, you drink, the air you breathe, everything is a chemical. So, what is a chemical? A chemical is made up of atoms and molecules. These are terms that are thrown about quite a bit. Okay, what are they? We're going to look at them in more depth. But for now, we're just going to say that atoms are very small particles, and molecules are combinations of those atoms that are in and of themselves small particles. And these atoms and molecules compose all of the common matter, all of the material around us. Okay, atoms are bound together by electrical interactions. That's something we'll be looking at later in the semester, to form different types of molecules. And then the thing that holds the atoms together, these electrical interactions, we refer to those as chemical bonds. So just looking at an example of this, if you have a soda in front of you, maybe you're drinking a soda while you go through this presentation. All of the soda is composed of these tiny particles called atoms. Okay, so if you have molecules, they break down into atoms. If you took a single drop of your soda, it would have about 1 billion trillion atoms. Okay, so that's a lot of atoms. And this number that you're seeing here, this 1 times 10 to the 9th power times 10 to the 12th power, that is putting it in terms of scientific notation. That's something else we'll be looking at, probably more in the scientific math, but we will be looking at that. So, soda pop contains these atoms. It's a mixture of what kind of atoms and molecules. One of the molecules in soda is carbon dioxide. Okay, that's a big player in soda. We'll look at what it does. Water molecules. So water is one of those dreaded chemicals that people talk about. Okay, and then a lot of other substances that are put into the soda to contribute to its color and its flavor and just make it more appealing. All right, so if we look at an image here of the soda, and then a drawing of the molecular view of what's in there. We see these two molecules that we have in here. Okay, so we want to identify those two molecules that we just talked about. We talked about carbon dioxide and we talked about water. Okay, so if we look at it, this one on the right represents the carbon dioxide. The black dot is representative of carbon, the red of oxygen. So carbon di is 2, oxide is oxygen. And we'll look at learning how to name compounds. So there's our carbon dioxide. This one represents a water molecule. So here's, we're using, again, oxygen for the red. And then these little whitish silvery ones are the hydrogens. So H2O, if you've heard that formula for water, H2O. From a molecular point of view, can we explain why soda pop fizzes? What is it about these molecules that makes it fizz? Okay. So, a can of soda pop is a chemical mixture. It consists primarily of that water and carbon dioxide and then sugar. We all know there's sugar in soda pop, so that's a molecule as well. The characteristics of these molecules give the soda its character. So the sugar molecules react with sensors on our tongue to produce sweetness. Okay. Carbon dioxide and water, those are in there, first of all, to make it a liquid, to have a carrier, lots of water in there. The carbon dioxide is in there to give it that fizzing action. Again, it's that sensation on the tongue that we like so much. Okay. So here's our carbon dioxide molecule. As I said, carbon in the middle, oxygen on either side, and they're held together in a straight line by their chemical bonds. Okay, so just keep that in mind for now. It's just a little straight line of spheres stuck together. If you took 3 little balls of Play-Doh and mashed them together, that's what you'd have. The characteristics of these molecules make carbon dioxide a gas at room temperature. Okay, so if you've ever heard of dry ice, that is frozen carbon dioxide. If I get it really cold, I can turn it to a solid, but in its room temperature state, it's a gas. Water also has 3 atoms. It's got 1 oxygen and 2 hydrogens, but instead of being straight like that carbon dioxide molecule, it's bent. Okay, and don't worry about why for now, but we'll talk about that as we get into a later chapter. Now, not because it's bent, but because of other characteristics of water, it's a liquid at room temperature, as we know. So you can have a glass of water. If we heat it up, it can convert to a gas. We cool it down, it converts to a solid. But at room temperature, it's a liquid. So why are these two fairly similar molecules, 3 atoms, one's in a line, one's bent? Why is one a why is one a liquid and one a gas at room temperature? These are all questions that we want to answer as we go through this semester. So the carbon dioxide, when we put that gas, that carbon dioxide under pressure, it forces the molecules to go into the water molecules. It forces them to interact and mix with the water molecules under a sealed container condition. So carbon dioxide is dissolved into water under high pressure. When I release that pressure, when I open a can or a bottle, the molecules no longer are forced into the water molecules. They can separate themselves and escape as bubbles. Okay, so we get these little pockets of bubbles. As those molecules of carbon dioxide come together, they form a pocket of gas that comes up out of your soda. All right, so chemicals compose ordinary things around us. There isn't anything that you can hold or touch, anything that has matter that is not made of chemicals. Okay? They make up virtually everything we come into contact with. There are a few exceptions, but if you can hold it, touch it, it's a chemical. Your soda, we already talked about. If you're writing with a pencil, pencil contains graphite. This represents graphite. It's nothing but carbon atoms that are attached together. Your skin has all these different atoms and molecules that make up your DNA. The paper in the book is made up of cellulose, the ink that's printed on there. These are all different chemicals. So we've already said a lot of people have a negative view when you say the word chemical. They have a very narrow view of it. They think a chemical is something that's a danger, a poison, a pollutant, something bad for you. Okay, so as chemists, something that we want to do is try to inform people of the broader scope of chemistry. Not just the bad things, but the good things too. The air we breathe, the water we drink, all the modern innovations that we have. Toothpaste, Tylenol, toilet paper, for heaven's sakes. Would we really want to go without that? That's a chemical. So chemistry is going to help us explain the properties, behavior, and makeup of various chemicals by understanding the molecules, the things, the little building blocks that everything is made up of. If we understand the building blocks, we can understand the larger character of something. Okay, so if we want to come down to a simple definition of chemistry, it's the science that tries to understand how matter behaves by studying how the atoms and molecules behave. And I'll go one step further on that, something that a lot of general chemistry textbooks don't tell you. Chemistry, unless you're talking nuclear chemistry, chemistry boils down to the interaction of electrons between those atoms and those molecules. We want to see where the electrons are going, and we'll be looking at that again as we get into the semester. So we want to talk a little bit about how scientists, not just chemists, but scientists approach their world. Okay? A chemist or any scientist will use the scientific method. And actually, it's not just scientists who use the scientific method. Almost everyone every day uses the scientific method to some extent. We just don't tend to put that term to it. It's rational thinking, critical thinking, a way of learning that is going to emphasize making observations and testing those observations to see what happens. Gathering information when you do that, and then using that to come up with a hypothesis, produce knowledge as the result of our senses. So we rely on our senses. The scientific method stands in contrast to the way the ancient Greeks did it and medieval applications. So ways of emphasizing reason to produce knowledge as the result of thoughts is what we want to focus on. All right, so as I said, we're going to make observations. What kind of observations? Well, we don't want to be too subjective. We don't want it to be based simply on one observer. So we want an observation that involves something that can be sensed or repeated by other people. So we need measurements. We need some sort of way to quantify the observation. We use those observations, then we test those observations to kind of start building up a hypothesis. The hypothesis is just kind of our explanation of the observations we already have. Well, I've noticed that this, and this happen, therefore I think they can be explained by this. Okay? Once you have a hypothesis, you're going to test that hypothesis. You're going to see, does it hold up, does it not? Once you have enough data that supports a hypothesis, you can begin to formulate a law. It just summarizes the results of lots of observations. And then eventually you can get to a theory, which is a model that explains a behavior and gives underlying causes for the observations that we've made. All right, so we can have a hypothesis, then a law, then a theory. Those all have to be tested over and over and over again. We validate them by experimenting on them. If we can't validate them, then we can't confirm them. Okay? So if a hypothesis is not confirmed, then we have to come up with a new hypothesis. We're going to change the idea. Okay, that didn't work. What about plan B? So we check that one out and we keep testing. So in reality, the whole process of the scientific method is really not ever to prove something. We can't ever definitely prove something. What we're trying to do is disprove our hypothesis. If we can disprove the hypothesis, then we know that one doesn't work and we can go on to the next one. But as long as we have a hypothesis that seems to hold up to experimentation, we just keep testing it and we grow from that. So we can expand our hypothesis into a law. We can expand that law into a theory, and then we keep testing it. We're always looking for new evidence to confirm or deny these. All right, so these observations, those are going to be critical to us as scientists. So how do we make those observations? Well, early on, those observations were simply made with the senses that we had at hand, with the naked eye, with what we could hear, what we could see, what we could taste, touch, smell. Over time, though, we began to refine our ability to make these observations. And so some come from experiments that rely on instrumentation. And instrumentation varies greatly. The focus of our chemical lab tech program is going to be learning how to use this sensitive instrumentation, but also how to rely on our senses to make those observations, to interpret the results from those instruments. Okay, so observation is going to usually involve the measurement or description of some aspect of the physical world. An example of that, Antoine Lavoisier was a French chemist in the 18th century, and he made a particular observation about the physical world around him. He studied combustion, which is, again, something very specific to a chemist, but for now, combustion is just burning something. Lavoisier measured the property of mass in the process of combustion. So what he wanted to know was, what was the effect on the mass of a substance of this process? The mass of an object is just the measure of quantity of matter within it. Now, we relate the mass of an object to its weight. That's how we're able to make an observation of that here on Earth. But the mass is really just how much stuff is in there. So what Lavoisier did was burn substances in a closed container so that all of the material remained in the container. None of the smoke, none of the ash, none of the gases could get away from that combustion. He would measure the mass of the container before he carried out the combustion and after, and notice that in a completely sealed container, there was no change in mass. Certainly, there was a change going on in that container. We know what happens when something burns. We know that there's heat. We know that there's smoke. There's ash that occurs, but the overall mass remained the same. That was an amazing set of observations to make for the time, because it seems like if you're just burning something, you've got a bonfire in the backyard, it seems like this big piece of wood, these charcoal briquettes, whatever you're burning, seem to disappear. They seem to go away. So the question was, where are they going? What's happening? Okay. So observations will lead scientists to formulate a hypothesis. Okay. Now, if it's a good hypothesis, it is falsifiable. So any of these hypotheses are that way. Further testing could prove you wrong. You want to keep testing. You keep designing experiments that are highly controlled observations where you're trying to either validate or invalidate your hypothesis. You want to see what effect one thing has on your experiment. Okay? So if the result of an experiment shows that there's a mistake in that hypothesis, then possibly it can be modified, changed slightly, or you may have to throw it out and start over. Okay? But whatever you do, you've got a new hypothesis now. That one also has to be tested. So it's a constant cycle for a scientist. We never say good enough. There's always somebody out there checking it. And then even if you think you've got it good enough, somebody else out there needs to be able to do the same thing you did and confirm those results. So again, that's going to be important to us looking at laboratory technology, because very often when you're working in those sort of environments in these industry labs, you're trying to prove or disprove something for someone else. And you may not be the only one doing it. A company, if it's something very sensitive, may have your lab, they may have 3 or 4 other labs all doing the same analysis on the same materials to make sure everybody is in agreement on that. All right, so if we get enough observations that all seem to support a hypothesis, then we go to a scientific law. In Lavoisier's case, enough people were able to verify his results that it developed into the law of conservation of mass, which simply states that for a chemical reaction, matter will neither be created nor destroyed. It can be changed, but you're not making anything brand new that never existed before. You're not making anything go out of existence. You're just changing the way you put it together. So it's kind of like having a box of Legos. You can have all the little pieces, and I can hook red Legos to blue Legos and have them put together. I can then pop them apart and put blue Legos with yellow Legos. I've still got the same blue Legos, it's just how I put them together. But overall, the red and the blue together are going to look different than the blue and the yellow together. Once we get our laws and we get them well established, these well established hypotheses, we can begin to develop a scientific theory. Okay, a theory is just a little bit broader and deeper way of looking at observations and laws. They're models for nature very often, and they predict behavior. So what we're trying to do is sort of use our observations, use our laws and our theories to make predictions about something else that we can then go test. All right, so here's an example. You can classify each of these statements as an observation, a law, or a theory. Okay, so I will let you go back and review these, and I will let you write those down and bring those with you to class on Friday, and we can take a look at those when you come in, when we do our recitation section. Okay, so make a note of that, take a look at these, tell me what you think. If you need to pause it right now to do that, go ahead. Here's just an overview of the scientific method. So if you're used to seeing things in a graphic form, you might find this a little bit easier to deal with than just me talking at you or a bunch of words on the screen. So you're going to start here with your observations. Okay, so for example, you've got the 2-year-old in the high chair, and they've got a bowl of Cheerios, and they make some observations. They say, when I take this bowl of Cheerios and I shove it off the high chair, it falls to the floor. And they start to think, and of course, again, maybe not quite this higher order, but they start to think, wonder what if that happens every time. So they get another bowl of Cheerios. Okay, they take their hypothesis. Every time I shove the bowl off the high chair, it falls to the floor, and they test it. Okay, shoved it off, fell to the floor. Confirm my hypothesis. Let's test it again. Next bowl of Cheerios, shove it on the floor. Look at that, it went down. Test again, and they keep going until it's confirmed for them that, yep, pretty much every time I shove that bowl of Cheerios, it's going to the floor. Okay, if they did it enough, hopefully you don't give them that many Cheerios. They start to go from hypothesis, law, theory, and then they go back into this cycle. They keep experimenting, they keep testing. So what happens if your findings don't support your law, your hypothesis, or your theory? Well, you can revise it, you can try again. Sometimes, though, it is just so flawed, poor theories just get eliminated. The good theories rise to the surface. So that's why scientific research is so important. It's very important to keep an open mind and to realize even if you think you know what's going on, you may not always know the whole story. There may be something that you haven't tested yet, that you haven't seen yet. So very important when you're doing experimentation to keep an open mind and realize that if something doesn't go the way you expect it to, that's not a bad thing. It's just another question. What happened? Can you figure out? Is this really invalidating? Does something go wrong? You just keep checking it out. Another example of scientific method was the development of the atomic theory of John Dalton. And basically, we just want to look at this idea of atomic theory. That's going to become important to us later, talking about atoms and molecules. So Dalton was explaining the law of conservation of mass that Lavoisier came up with by proposing that matter was composed of atoms. Okay, so we take it for granted now that everything is made up of these tiny little particles called atoms. But in Dalton's time, this was totally revolutionary. They didn't know about these little particles. They had other theories. There were lots of theories out there. Okay, he was able to test. Okay, it was a model of the physical world. It was tested and it held up over time. So because it held up consistently over and over and over again, it went beyond just simple observations, hypotheses, laws, okay? Or it went past those to the idea of this theory. It was able to explain all the different laws and observations. It's sort of the blanket that tied everything together. Here's a law, here's a law, here's a law. How do we explain those? These things called atoms. Those can explain why these laws are there. Okay, so to have a theory, you have to have a lot of really strong support for that. Experimental support, very powerful pieces of scientific knowledge. So you'll very often hear people say, when they hear about something, oh, that's just a theory, as if theory was just a speculation. So global warming, oh, that's just a theory. Well, what they probably mean is that's just a hypothesis. That's just an idea. It's still being tested. Theories are a lot stronger than that. Well-tested theories are about as close to as we get to an absolute truth. Okay? So if you hear something listed as a theory, you can pretty much bet that for what we have right now, it holds. It explains a lot of different things. So this idea of atomic theory, what are these little things? What are atoms? Because no one was able to see them. They were so small. So the idea that all matter is made up of atoms, it's a theory that we've had for about 200 years. And we've got 200 years of experimental evidence to go with it. And we had to kind of take it on faith, not faith, if you will, but the data that we had, the experiments that we had, were observations of things going on. We never actually saw an atom. We saw the effects of atoms. We saw the evidence of atoms. It's like seeing a fingerprint without actually seeing a person. But now we actually have technology that lets us see the atoms themselves. Okay, so this was one of the first pictures ever taken of individual atoms. And it's in kanji, it's kanji characters, and it spells out in kanji the word atom. And it's made with individual iron atoms. So each one of these little dots is an iron atom spelling out atom. Okay, and they're deposited on a copper surface. So this is really a cool picture for us as chemists. Okay, so just know that in order to be successful in chemistry, it's a little bit like going back to your childhood. You want to be curious, you want to use your imagination, and you have to want to know why. If you talk to most chemists, they'll tie it back to that moment somewhere where they kept asking why. They wanted to know why. They were just so curious they couldn't let it go. That's what happens to us in chemistry. Unfortunately, chemistry also requires calculation, the ability to quantify things, to make those observations. So we will have quantitative data and qualitative data, and the quantification is what we're focusing on. Now, I'm not going to talk a huge amount about that here because that's what your scientific math course is for, but be aware that it will be crucial to both parts of the courses this semester. Okay, so quantification just involves measurement as a part of your observations. It's one of our most important tools. It allows you to specify differences very precisely, better than we can do with our senses. So for example, if you've got 2 cups of hot water and you pick them up, your hand may not be able to detect a difference between 2 cups of hot water as you're holding it. But if you actually take thermometers and measure the temperatures, you may find that they're 4 degrees apart. 4 degrees Celsius, we're going to be using the metric system and scientific measurements in this course, so we'll talk about those in Chapter 2. Okay. But there might be a difference that you can't sense, so we need those instruments in order to make those measurements. Okay, now as we're going along, just to let you know about the textbook. The homework that I'll be assigning will be in the Mastering or the Conceptual Chemistry websites, since this is going to be a hybrid course. But if you want to get a little extra practice from the book, the answers to all the questions that are numbered in blue appear in the back of the book or appear in that section of the ebook. Problems that occur within the chapter, the exercises in the problem section are paired. So the answer to the odd-numbered exercises appear in the answered section in the back of the book for those. Okay, so questions, problems, if they're in blue, those answers are in the back of the book. All right, so just to kind of wrap up Chapter 1, what you need to get out of this chapter. First of all, the idea of matter and molecules. What is chemistry? The other one is the scientific method. What are the steps of that and how do we use that process? And then we also talked about the law of conservation of mass and Dalton's atomic theory. So keep those in mind as we go into Chapter 2.